this TTH-associated production and in the Higgs to 2 photons decay channel. So it was more or less between 2018 and 2020 that this work began. And of course, in this talk, I will cover obviously a particle physics analysis of experimental data that come to us from the proton collisions at the LHC. And what we care about the most are measuring the properties of standard model particles, in particular the Higgs boson. And what we focus on is the interaction between the Higgs boson and the top quarks in TTH and TH associated production. And here I will tell you about the first measurements that we did of differential cross-section and charge parity properties in this in TTH with Higgs to BB. So first, a brief timeline of the LHC. So right now we are here in 2023, and in 2018 we finished what we call run 2, in which we accumulated a total of 139 inverse von Barn of data. And so up to now, from the Higgs discovery up to 2018, what we've been doing is analyze this combined data set and doing the best precision measurements that we can of the Higgs boson couplings, production processes, and decay channels. So the landscape at the moment is the one that you see summarized in these plots. We have measured the cross sections and branching ratios of almost all of the production processes and decay channels using the full run 2 data set. And this is what you see on the left for the production processes and on the right for the decay modes. And you can see the uncertainties are quite small and all the results are very much in agreement with the standard model. And you see that we still have left to measure single top associated production and the decays of Higgs to Z gamma and Higgs to muons. And this is within reach, maybe at 3 sigma of the full LHC dataset, maybe with a high luminosity phase as well. And so right now, what we are doing is that we extensively use what we call a simplified template cross-section framework, in which we measure the cross-section not only inclusively in the entire phase space, but in bins of dedicated variables, usually the Higgs boson transverse momenta, but there's also invariant masses. And this is something that is agreed upon between experimentalists and theorists, and it allows us to have a more apples-to-apples comparison between theory and experiment, and also reduce some of the theory uncertainties in our measurements. And of course, now we know that the Higgs boson couples to the mass as predicted by the standard model. But not only can we do this, we can also do more detailed measurements in which we can start to probe the actual quantum structure of the couplings of the Higgs boson. And we do this mainly in 2 different ways. When it comes to fermions, we know that potential new physics effects can affect the interactions already at 3 level. So we use a simplified parameterization that I will mention a few slides later to set limits on a pure CP-odd Higgs boson. And at the moment, the best measurements that we have are around 3 sigma, meaning that we have evidence that the Higgs boson is not a pure CP-odd particle at 3 sigma. And this is an example of the measurement of Higgs to tau tau. And then in the case of bosons, we know that new physics effects usually come from, or can be parameterized as coming from operators with a dimension above 4. And so what we do is we use effective field theory to study these couplings. And then what we do is set limits on the effective field theory coefficients. And this is an example from Higgs to ZZ, where this is the value of this is what we call the Wilson coefficient for CP-odd ZZ coupling. And here you can see the exclusion limits that we have on this coupling alone. So in this talk, I will focus on the properties of the top Yukawa coupling, so the interaction between the Higgs boson and the top quark. And I will mention 2 analyses to which I have contributed. So the first ones are TTH analysis with Higgs to BB, and this includes 2 of them. A cross-section measurement in the simplified template cross-section framework, and also a direct measurement of the charge parity properties of the coupling. And then, because these analyses are highly impacted by the background of TT bar production with additional B and C jets, I have contributed to the measurement of the cross-section of TT bar plus additional C jets. And this is also the first time that we have done this measurement in Atlas. Of course, we are also measuring TT bar plus B jets, but I will not cover it here. So on the TTH analysis, I will go through motivation and overview. I will tell you how we extract the CP information, what is the event topology that we are looking at, which backgrounds affect our searches. I will cover the event selection strategy, the results, and systematic uncertainties. So the main goal of my work specifically has always been to measure the charge parity properties of the Yukawa coupling. But first we need to take a bit of a step back or a detour to measure the cross-section of TTH with Higgs-2BB. And as I said, we now do this in bins of the transverse Higgs boson momenta in the STXS framework. And the reason for this is because we have access to a lot more data. We have the full run-2 dataset, so we can do more granular measurements. And then it's also an important stepping stone on top of which we can build the CP analysis. So these are two separate analyses, but they have a lot in common. For example, data and Monte Carlo samples, object reconstruction, the event selection, statistical analysis, and mostly the way in which we treat the systematic uncertainties. One of the key differences is the way in which we treat single top Higgs-associated production. And the reason for this is that TH has a very small cross-section in the standard model, but in CP-odd and CP-mixed scenarios, it increases a lot, the cross-section. And the cross-section itself is sensitive to the sign of the coupling. And this is what you see on this plot here. So on the y-axis, you see the cross-section. On the x-axis, you see alpha, which is a CP mixing angle. And you see the cross-section for TTH in red and for TH in blue. And you can see that TTH is symmetric around alpha 90 degrees, while TH is anti-symmetric. And so this means that in the CP analysis, we treat TH as a signal, and in the STXS analysis, this is a background. When we want to extract the CP information, we use the following parameterization shown here that has two terms. One that is proportional to cosine of alpha. Alpha here is a CP mixing angle, and this is the standard model term, CP even. And then we have a term proportional to the sine of alpha that is a CP odd or beyond the standard model term. And then we have what we call kappa T, which is an overall coupling modifier that basically just modifies the strength of the coupling. And then what we do is, based on this, we calculate the number of events in each bin of our analysis as a function of the CP mixing parameters, and we do the ratio with respect to the standard model prediction. And then in TTH, which is here on the left in pink, you see that the expression is fairly simple. And this is mainly because we can neglect the interference between the CP even part and the CP odd part. And this is, we have demonstrated at truth level using Monte Carlo samples that this is the case. But for TH, that you see on the right, it is a more complicated expression. You see that the CP even and CP odd interference cannot be neglected, at least not at next leading order. And then we also have the interference between the diagrams in which the Higgs boson comes from the top quark and the diagrams in which it comes from the W boson. And so these are these two terms here. And then in the end, in the actual analysis, what we do is extract these coefficients from a bunch of Monte Carlo samples that are simulated with different values of alpha and kappa T, and then we do a fit to the yield of all of these samples, and we are able to extract these coefficients. And we have to do this for each bin of our analysis. This is what the TTH event looks like in a very naive way, but you can see already that this is a very complex event topology, mainly because there are many particles in the final state, and this happens because we have two top quarks, and then each top quark decays to a W boson and a B quark. And then what happens is that we have two W bosons, and they can both decay leptonically, in which case we say we are in the dileptonic channel, in which we have exactly two charged leptons, or one can decay hadronically and the other leptonically. And in this case, we are in the semi-leptonic channel where we have only one charged lepton, but we have more jets. And then in this analysis, we also consider what we call the boosted regime, in which the Higgs boson has a larger transverse momentum. And so the decay products, meaning the two big quarks, are reconstructed as a single large radius jet. And so then all of these channels are optimized independently, but they are taken together in the statistical analysis. In this analysis, the dominant background is TT bar production with additional B jets mainly. This is what we call TTB. And both the signal and background, the contribution from signal and background is estimated from Monte Carlo simulation. The small exception is that the TTB cross-section is measured directly from data in the fit regions as a free-floating parameter in our fit. And so here on the left, you see one of the Feynman diagrams for TT bar production with two additional B jets. That is an irreducible background to this analysis, and therefore it's the dominant contribution in the signal regions. And on the right, you can see examples of signal regions here and control regions here. And you see that TTB, this dark blue or purple, is the dominant contribution in all of them. And in some of them, we have a somewhat large contribution already from TTC and TT light. And then every other background, there is the yellow and the green are subdominant. And here, these are from the cross-section analysis, and so TH here is a background, and you can see that it is nowhere to be seen in this plot. So it's a really a very small contribution in the standard model. Because we have such a complex final state, this analysis relies heavily on multivariate methods, and we use them mainly in two steps of the analysis. In the reconstruction, and by reconstruction what we mean is taking the final state particles, combine them together to get the momentum of the intermediate particles, the W's, the tops, and the Higgs boson. And so for this we use either a BDT or a boosted neural network, depending on if we are in the resolved or in the boosted regime. And then we can take the three momentum of these intermediate particles and construct variables that allow for further discrimination between signal and background, and use them as input to what we call a classification BDT. So this is trained to separate TTH CP even from the backgrounds. And then it's used in two ways. In the cross-section analysis, it is used as the final discriminant in the signal regions, and in the CP analysis, it is used to split the events into regions with increasingly higher percentage of signal or TTH. In the end, what we do, or what we start by doing, is taking the events and split them into channels, the ones that I mentioned a few slides ago, and then we assign them to orthogonal signal and control regions that are split based on number of jets and the number of beat jets. And this is what is summarized on the table here. So the control regions in pink, they are common between the cross-section and the CP analysis, meaning that they are used in the exact same way in the two fits. And then the signal regions, which are in orange, they are further subdivided in different ways in the cross-section and in the CP analysis. In the cross-section analysis, we split the events based on bins of the reconstructed Higgs boson PT. And in the CP analysis, we split them in bins of the classification BDT that I mentioned the slide before. In the end, what we do is to perform a simultaneous maximum likelihood fit, including all signal and control regions. And once again, these are two independent fits, one for the cross-section and one for the charge parity analysis. In the control regions, we fit either the event yield or the average delta R between pairs of B-jets. And this allows us to constrain the shape of the backgrounds. And you see an example of such a distribution here on the right. So these types of plots, they show you on the y-axis the number of events per bin. On the x-axis, the value of a given variable, in this case, delta RBB. You see the field stacked histogram shows the total contribution of the backgrounds and the signal. The signal is in red here. And then you see the dashed red line shows the shape of the signal with the cross-section normalized to the total background yield. And then the black points are data. And on the bottom pad, you see the ratio between data and the total prediction from Monte Carlo. In the signal regions, in the cross-section measurement, we fit the output of the discriminant of the classification BDT, which is the plot here on the left, where you clearly see the separation between signal in red and the backgrounds in blue. And in the CP analysis, we fit a CP-sensitive variable. Here you see an example. This is a variable called B4. And here instead what you see is the separation between TTH and TH CP even, which is the red dashed line, and the CP odd, which is the blue dashed line. So here we use two different variables depending on the channel, dilepton or single lepton. They are called B4 and B2. They were proposed in literature a few years ago. And they are basically products between the momenta of pairs of particles. In this case, we use the top quarks, so the top and the anti-top quark. This brings me to the results from the cross-section measurement. So the statistical significance for observing TTH, the Higgs BB, is 1 sigma observed, while 2.7 sigma was expected. Of course, this means that we cannot claim evidence for this process in this channel alone. But of course, we know that TTH exists because we have measured it, and we know that Higgs BB exists because we have measured it. So it still makes sense to calculate the signal strength independently in this channel. And this is what you see on the plot below. On the last line, you see what we call the inclusive signal strength that is measured as a single value in all of the analysis regions. And it is measured to be 0.35 plus or minus 0.35, which of course shows a downward fluctuation with respect to what we'd expect in the standard model, which is 1. And then we also do the actual STXS measurement, in which we measure one value of the signal strength in each bin of the Higgs PT, But this is measured from a single fit, right? So there's a single fit with 5 free parameters, one for each Higgs PT beam. And here you can see that in some beams, of course, there's a downward fluctuation with respect to the standard model prediction. Nonetheless, the precision that we have in most beams is fairly good, even though there is then the downward fluctuation. We also measure, as I mentioned, the normalization factor of the dominant TTB background, and this is measured to be 1.28 plus or minus 0.08. And so here, of course, we also have, let's say, a difference with respect to what we expect in the standard model. And this is something that we have seen across a variety of analyses, and we know this is most likely a problem with our Monte Carlo generators. We then also calculate the 95% confidence per limit on the cross-section for TTH, both inclusively corresponding to this signal strength and in the different beams of the Higgs boson transverse momentum. In the CP analysis, the main result that we get is the value of the CP mixing angle alpha. It is measured to be 11 degrees with a very large uncertainty, and therefore it is still very much compatible with the standard model. And we calculate what we call the CP odd exclusion significance, that is 1.2 sigma. So once again here, you see that we cannot say that we have evidence to exclude CP odd production, but it is disfavored with this level of significance. In this type of analysis, what we show the results in the form of this two-dimensional plot that shows on the y-axis the CP odd component of the coupling, and on the x-axis the CP even component. And you can see the best fit value is this blue star, and you can see that it is very close to the standard model prediction, which is this red star here. And then you can see the different exclusion limits in these colors that go outwards. And once again here we measure the normalization factor that is very compatible with the one that we measured in the cross-section analysis, as it should, because these are the same events and this is the same background modeling. And here on the right, I want to highlight that the boosted region that is also included as a single region is very important for a couple of reasons. The first, you see from the dashed lines here that CP odd has an increased acceptance in this region, as we already know, right? Because the CP odd events are known to have more forward topologies, meaning the larger transverse momentum of the Higgs itself. And then you can also see here, this dark blue shows the TH CP odd component, and you can see that in the boosted region is where there's a larger increase for TH. And so this highlights both the importance of exploring the boosted regime and also the importance of taking TH into account in these types of measurements. Now I want to briefly discuss the systematic uncertainties in this analysis, because these are really a limiting factor for us here. These analyses are dominated by the uncertainties on the modeling of the dominant TTB background. So you can see on the left here what we call a ranking plot. This shows you for each systematic uncertainty the impact that it has on the signal strength, of course ordered. And you can see that the top 6 or 7 here relate to the TTB background. And the problem here is mainly, we know that our Monte Carlo has some problems, but it's also very hard in this analysis to find a control region that is very pure in this type of background without having much signal. So as far as I know, it's not possible at the moment, or there's not an accepted method to do a data-driven background estimation, which would be very valuable here, because it would be, I think it would make it easier to control this background. But unfortunately, at the moment, we are not at the point where we can do this, so we need to continue to rely on Monte Carlo simulation. Following the modeling uncertainties, we have experimental uncertainties, of course. They are subdominant, but among them, the largest contribution comes from B-tagging efficiency and the C and light jets mistag rates. But this is very much a subdominant uncertainty. On the CP analysis, the things that I just mentioned continue to apply, but there are some additional work that was done here. So we include an additional systematic that compares 2 TTB predictions calculated with 4 or 5 quark flavors in the PDFs. This is what we call 4 and 5 flavor scheme calculations. And the reason for this is that we have seen that the difference in the shape between these 2 calculation schemes was not captured by any of the other modeling systematics that we already have. And so there were some fears that we could be biasing the signal extraction. Also in the CP analysis, we developed an alternative method to rank the systematic uncertainties. maybe if there are questions, I can go into more detail as to why we needed to do this. But the way this method works is that for each systematic, we remove it from the fit and we rerun the fit again, and then we reproduce the likelihood scan, and then we see how much does the uncertainty on the parameter of interest changes when removing that systematic. So if it changes more, means that systematic has a larger impact on our parameter of interest. And this is what you see represented here on the left. This brings me to the end of this part. I've shown you the results of the first measurements of Higgs boson production in association with top quarks and decaying to big quarks. These measurements are largely impacted by the TTB background, in particular TTBB, and they are very, very challenging channels. And so we have a low sensitivity in this channel by itself, but it is a very important channel because it brings sensitivity in the higher Higgs boson transverse momentum regime, where other channels don't have enough statistics. For example, Higgs to gamma gamma, the spectrum of the PT of the gamma gamma pair falls much quicker than if you look at the PT spectrum of Higgs to BB, for example. And so these analyses are important when we do the combined Higgs measurements, because we can access corners of the phase space that are not covered otherwise. Specifically to the charge parity measurement, we have introduced novel and powerful CP-sensitive angular variables that we have used as our final fit discriminant. And as I already mentioned, we have confirmed that single top Higgs production is extremely important for these types of studies. Another very important thing is to further explore the boosted regime. I would like to now tell you about the cross-section of TT bar production with additional C-jets. As I already mentioned, this is an important background for these measurements, and it's also something that has not been measured before in ATLAS, and it has been measured by CMS. I will go through the motivation and overview. I will tell you how we identify heavy flavor jets, in particular how we separate B jets from C jets. This is an important thing in this analysis. And then event selection and the analysis strategy, and of course the results. I already mentioned this is an important background for TTH analysis in all hadronic final states, but it becomes especially important if I tell you that in the ongoing analysis that we are doing of TTH with Higgs to BB, this is what we call the legacy analysis. I will say a few more words in the end. But here in this new analysis, we use a loser preselection. And this means, oops, sorry. We use a loser preselection, and this means that we have a larger contamination of other backgrounds that are not TTBB. So we have more TTC and we have more TT light. So this means we need to have ways of controlling these backgrounds better, which is something that was not so much, we didn't study it in so much detail in the previous analysis because TTBB was absolutely the dominant one and everything else was much smaller, but this is no longer the case. And of course, this is an important measurement because it allows us to tune our Monte Carlo generators. And this is something that there has not been as much investigation in TTCC as it has been in TTB, but I expect that in the coming years, there will be more investment, both experimental and theoretical. And so it's good that theory will help us. So we also want to have the measurements to be able to help our theory friends. And this measurement has been done by CMS, but not yet by ATLAS. So what we set out to do here is to measure the signal strengths of TT1C and TT2C. My work concerned specifically the dilepton channel. This channel allows for a better separation between TT light and TTC because it does not have C jets coming from the decay of the W boson. And this is something that happens in the single lepton channel, so it's harder to disentangle pure TT bar plus C jets. Of course, dilepton has a reduced statistical power, and this is exactly why we are now working on the combination with the single lepton channel. We developed a dedicated C-tagging algorithm to improve the sensitivity of the analysis. And as I said, we are doing the combination and the documentation exists only internally at the moment. So how do we do the C-tagging? We start from the ATLAS standard B-tagging algorithm. This is a multivariate algorithm that outputs 3 probabilities, the probability of a jet being a B jet, a C jet, or a light jet. And then based on these probabilities, we construct discriminants. Discriminants that allow us to separate B jets from light and C jets, or that allow us to discriminate C jets against B and light jets. And then if we plot the output of these discriminants in a two-dimensional plot, this is what we get. You see in the different colors, the different types of jets identified at truth level. So this is from a Monte Carlo sample. And you can see in blue here, the light jets. In green, you can see the B jets. And then in orange, a little bit spread out all over the place, you see the C jets. And so this shows you exactly why you need this extra C tagging axis. Because if you look just at the y-axis, you can see that B jets and light jets are very well separated. So just using this axis would be enough. But for C jets, this is clearly not the case. And in particular, they are concentrated more on the right side of this plot. So then what we do is define 5 bins in this plot, one very small here at the top, a little bit and below one that is slightly larger. And these are what we call the B tagging bins. So the jets falling there have a high probability of being an actual B jet. Here, this big bin are the light or untagged jets. And then everything on the right is what we call C jets with different efficiencies. And then here on this table, you can see for each working point, also the rejection that we get against the other two types of jets. So for example, for the C jets, you see the B rejection is around 30 or 20. And the light rejection is around 1000 or 100, depending on the efficiency that we choose. And then what we do is we calibrate these bins as we would for the standard Atlas B tagging algorithm, where here calibrate means adjust the efficiency measured in data and in Monte Carlo to make sure that they match. So calculating scale factors. The analysis strategy then follows like this. We select events with single lepton triggers. And of course, we require exactly 2 leptons because this is a dilepton channel. And then we apply a preselection that requires at least 3 jets, at least 2 B jets with a 70% working point of the algorithm that I mentioned in the previous slide. And then we divide the phase space that comes from this preselection into orthogonal regions based on the number of B jets, C jets, and all jets. And this is what is summarized on the table below. And you can see we have a total of 9 regions. Some of them have 3 jets and some of them have 4 jets. And then they have different number of B jets and C jets. So here in the regions, in some regions, we require exactly 0 C jets. And this brings us regions that are enriched in TT light. So these are TT light control regions. In the signal regions, we require exactly 1 or at least 2 C jets. And these, of course, work as signal regions and have more TT1C and TT2C. And then in the remaining regions, we have different requirements on the number of B jets at 70 or 60% working point. And these work as TTB control regions with different amounts of TT1B and TT2B. And you can see why, for example, in this plot. So this plot shows events with at least 4 jets and at least 3 Bs at 70% working point. And on the x-axis, you see the number of B jets at the 60% working point. And you see that if you place a cut here between these 2 larger bins, to the right, you get a larger contribution from TTBB, while to the left, you have maybe a larger contribution from TTB. So this is the main idea, to get different amounts of TT1B and TT2B so that we can independently control the normalizations and the shapes of these backgrounds. In terms of results, once again, we do a simultaneous maximum likelihood fit in all of the regions. In the control regions, we use just the number of events. In the 3 jet signal regions that you see on the left, these are regions enriched in TT1C, and we fit the invariant mass between the leading C jet and the closest jet in delta R. And in the 4 jet signal regions that you see on the right, they are enriched in TT plus at least 2 C jets, and we fit the number of jets. And these variables, they were chosen for consistency with what is done in the single lepton channel, but also to reduce tensions in the statistical model while keeping a high signal sensitivity. And then on the right, you see one of the main results. We measure the background normalization factors for TT light and for TTB. And we measure the signal strength for TT2C and TT1C. So here, of course, in these 2 parameters, we see a tension with respect to the prediction. This tension is around 1 sigma for TT2C and around 3 sigma for TT1C. So this is something that okay, of course, it is expected. That is not exactly the standard model prediction, but it is something that can be used as input for Monte Carlo simulation. And also at least to start a conversation with theorists to understand what exactly can we measure further that will help them in their calculations. This brings me to the end of this part. I have shown you the first cross-section measurement done by Atlas of TT bar production with additional seed jets. This is an important measurement for the further development of Monte Carlo generators. And I think in this particular moment, this is an important measurement because C-tag jets, so TT bar with additional C-tag jets, is becoming a more important background in the current analysis that we are doing. Exactly because we are opening up the phase space and having a larger contribution from these processes that was not the case in the previous analysis. Now I just want to close with a little bit of an outlook, like what does the near future hold? Also, what are we doing at the moment, and what do I see that we can do in the next couple of years, let's say? One of the things that we are currently doing is what we call the legacy TTH with Higgs-to-BB analysis. Legacy is a word that we use to say that these results will be the reference results from Atlas in this channel with a full run-to data set. So in principle, it's the best that we can do at this moment with a state-of-the-art reconstruction, B-tagging, and all of that. So this analysis benefits from improvements in jet reconstruction. We use the particle flow algorithm and heavy flavor identification. So we have new multivariate algorithms used to separate B jets from light and C jets. This will be the first analysis that has a fully consistent model of the dominant TTB background using 4 flavor scheme samples. The reason for this is the analysis that I mentioned before. They used as nominal the TTB background, the TTB 4 flavor scheme background prediction, but the systematics are calculated in such a way that we compare 2 alternative samples in the 5 flavor scheme, and we transfer the relative uncertainty to the 4 flavor scheme samples. So of course, this is a little bit of a patch kind of thing that is not ideal. And of course, there's always the risk that we are overestimating the systematic uncertainties. So I think that in itself, it will be good to have a fully consistent result with these samples that now are obviously available. And as I already mentioned, we now have a looser preselection, and we have more modern multi-class neural networks. And these neural networks, what they do is they use very simple variables, just the four-momenta of particles and then B-tagging score, basically. And then they have multiple nodes, and they assign events to either control regions, for example, TTC, TT light, and TTB control regions. And then in the signal region, in the same network, they do the classification into the different beams of the Higgs transverse momenta. So here, the good part of this is that of course, we do everything at once, but also we are not so dependent of mismodeling of more complex variables, which is a problem in the previous analysis because we use ability with many variables. Some of them are angular variables, and in some cases, even though we check the modeling, we know that there are some mismodelings in these variables, which is of course not ideal when training a multivariate method. So what will we get out of this analysis that we haven't seen before? We will have sensitivity to the lowest STXS bin between 0 and 60 GeV, and this could not be resolved in the previous analysis. So we measured 0 to 120 altogether, and now we can split this in 2. And we will have an increased sensitivity both inclusively and all of the STXS bins. I don't think I can show you the results yet because this is still Atlas internal, so I will not. But the uncertainties will be better than in the previous result. And then, as I already said, this will be the first result with a fully consistent 4 flavor scheme TTBB background modeling. And this is additionally interesting because CMS recently measured this exact channel using as well TTBB in the 4 flavor scheme, actually with a sample that has the generation parameters are very similar to the ones used in Atlas. Maybe they are even the same because the 2 experiments made a big effort to harmonize the 2. And they have measured TTH with Higgs-to-BB. And what you can see here, these are the different channels, fully hadronic, semi-leptonic, and dileptonic, and these are the data taking years. And what you can see here is that when you do the combined measurement, you get a value that is very similar to what we already obtained by Atlas in the previous run-to analysis. So here this brings the question, is this really a problem with the way we are modeling our background? Which I would guess yes. but I think it will be good to have the confirmation with both experiments, and then we can further investigate what is going on with these samples or with this calculation that we are not really taking into account properly in the analysis, because it seems to be more than just a downward fluctuation if it's in the two experiments. And then concerning the charge parity properties or the CP structure, these are two things that I think will be interesting in the future. One of them is to do Higgs combined measurements in the EFT framework, in the effective field theory framework, but with the goal of setting limits on CP-odd operators. So effective field theory is, we take the standard model Lagrangian and we augment it with higher dimension operators that are built only from the standard model fields. And then they are, of course, suppressed by the scale of new physics, and to each operator corresponds a coefficient that we call the Wilson coefficients. So then what we do in these Higgs combinations is to set limits on these coefficients. And we have done this for the CP-even operators. So we took basically all of the Higgs measurements that we have, we do a big statistical combination, and because we have a lot of data, we can have sensitivity to many free parameters, which is not the case in the individual analysis. So at the moment, there are plans within Atlas to do something similar, but for the CP-odd operators. And I think this will be a very interesting thing to see. Because independently, each of these channels is affected by multiple operators. And so it means that independently, they don't have enough sensitivity to constrain them that much. But if you put them together with other analyses, because multiple coefficients contribute to multiple processes, then we start to have some sensitivity to this very large number of parameters. And then another thing that I think is important is to continue to optimize CP analysis. And here there are multiple ideas or multiple things that we can do. We can do something similar to STXS, but in bins of angular variables or some other variables that are sensitive to CP, and we can agree between the different channels and between theory and experiment. And so we can express the results in a more consistent way. And then, of course, we can use this as input to this CP-odd combination that I mentioned. In each of the channels independently, we can start focusing more in the boosted regime, where we know that we will have sensitivity. And this is maybe specific to TTH Higgs to BB, for example. Because, for example, in the boosted regime, one thing that Atlas hasn't done that CMS has is TTH allodranic, which in the boosted regime seems a bit more feasible than in the resolved one. And this could also bring some very interesting sensitivity to CP that we have not explored at all in Atlas. Then we can take a look at what we call pure CP-odd observables. These are observables that they are supposed to have the best possible sensitivity to CP because they vanish in the case of a pure CP even. So we can measure an asymmetry or some sort of shape and hopefully increase the sensitivity of individual channels. And then, for example, this is once again specific to TTH. We now start to have analyses that are dedicated to single top Higgs production. Because in the analysis that I mentioned in this talk, the analysis strategy was driven by TTH because it's the thing that we know exists because we have measured it. So we focus on that. The thing is that TH has, for example, more forward jets. And so there's a big region of the phase space for TH production that is not taken into account in the TTH standard analysis, let's say, because we don't consider jets with an eta above 2.5. So it's important to have analyses that are dedicated, specifically optimized for TTH and TH or for TH alone. And these are things that we are already doing in the Higgs-top group in Atlas. This brings me to the end. I think I've shown you that associated production of Higgs boson with top quarks is a very challenging channel. It is also a very interesting channel, specifically for CP studies, because we only have fermionic couplings in the production and the decay. And there's no loops, and therefore, at leading order, there's no particles running around in the loops that might complicate the interpretation. The Higgs to BB decay channel specifically suffers from large combinatorial background due to the large number of jets and B-jets in the final state. So this requires multivariate techniques in the analysis. There is a very large contribution from the irreducible TTBB background. And because, as I told you, it's very hard to do a data-driven estimate, so we need to rely on Monte Carlo. And this then leads to the fact that we become severely impacted by the modeling systematics of this background, mainly from this background. Because of all of this, I think it's crucial to measure the dominant TT bar production with additional heavy flavor jets, TTBB and TTCC, And these are things that are currently being done in both of the experiments, both inclusively and differentially in many different observables. And hopefully I've shown you that the near future will bring interesting results in TTH with Higgs BB alone, and also for a broader spectra of charge parity studies. Thank you.